Okay, so we are looking at this A star algorithm, and in the last class we saw that the algorithm is admissible provided the heuristic function underestimates the distance to the goal, and provided every edge has a cost which is greater than some small value epsilon, and there is finite branching. We also saw that if two nodes, if there are two heuristic functions, one of them is more informed than the other, which means h 2 of n is greater than h 1 of n for every n, then we said that the algorithm A 2 which uses H 2 or A 2 star which uses H 2 is will explore a smaller search space, which we can depict as follows. Right, if this is a start node and this is the goal node, then one algorithm will search something like this and the other algorithm will search something like this. So, this would be H 2 and this would be H 1. So, this is what we expect, that the more informed heuristic function will be more focused towards the goal. So, it will search less away from the goal, whereas what branch and bound would have searched would have been a full sort of circle around that of that length essentially. So, the fact that we are using a heuristic function actually focuses the search towards the goal, and the more informed the heuristic function is, the more it focuses towards the goal, which means the search kind of becomes narrower and narrower. With a perfect heuristic function, the search would be just one path that it will explore essentially. Unfortunately, we do not have perfect heuristic functions. So, we try to look for as good functions as possible essentially, which means that the heuristic value must be as high as possible, but it should not cross the level of the optimal value essentially. So, for example, in the 8 puzzle, it has been observed that if there are two tiles, let us say 8 and 5, and they should be reversed, let us say in the goal situation, that 5 and 8 are here, but they should be 5 and 8 instead of 8 and 5. Then one of the functions that we saw was to simply count how many tiles are out of place, in which case 2 tiles are out of place, both 8 and 5 are out of place. The other function that we saw was a Manhattan distance function, which said that you would need one step to take 8 to this position, and you will take one step to get 5 to this position. So, the cost would be 2 essentially, or the contribution of these 2 tiles would be 2 essentially. Now, if you have solved this 8 puzzle kind of thing, you know that you cannot exchange them essentially. If you want to interchange the position of 2 tiles, you have to do some roundabout movement. So, you will need to add a certain value to that essentially. So, about 7-8 years ago, somebody enhanced the heuristic function to count for such things, that they are in the correct row, but in the wrong order. Then you add a certain amount, and that search was able to find the optimal solutions much faster for bigger problems, which means for the 15 puzzle and the 24 puzzle as well essentially. Now, today we want to look at another property, which is that consider two nodes. So, consider some paths to the goal node and two nodes m and n on the path essentially connected by that. So, if we take any such two nodes in the search space, and if they satisfy this property, that h of m minus h of n is less than or equal to k of m n, in a sense you can think of this as saying that it underestimates the cost of every edge which is on the path to the goal essentially. Rather, so h of m says that it is an estimate to the from m to goal, h of n says the estimate from n to goal, and h of m minus h of n in some sense is the estimate of the edge cost from m to n, and if this is less than the actual edge cost, in some sense we are saying that it is underestimating the edge, every edge cost essentially. This condition is called the monotone or consistency condition. And what we want to show is that if this condition is satisfied, which means that it is a property of the heuristic function. The heuristic function is such that this property is satisfied for any two nodes which are connected like this. Whenever A star picks a node n, it has already found an optimal path to n. We want to show this, we will do that in a moment. So, first let us look at what this is saying and what is the implication of this essentially. We are saying that under certain conditions, which is this fact that the heuristic function satisfies this condition, which is called the monotone or consistency condition. If this is satisfied, if the heuristic function is such that it satisfies this property, then the algorithm which is using that A star which is using that heuristic function, whenever it picks a node, any node n, picks meaning it picks from open, right, it has already found an optimal path to n essentially. So, what is the implication of this on our algorithm? If you look at, if you think about the A star algorithm, what does it do after it picks a node n? It checks for whether it is a goal or not. If it is not a goal, it generates its children, and the children are of three kinds, either new nodes or nodes on open or nodes on closed. And for nodes on which are on open and closed, it checks whether it has found a new better path, and for nodes on closed, if it has found a better path, it has to propagate that improvement to its children essentially. So, the implication of this statement, if this statement were to be true, it means that it has, the moment it puts a node into closed, it has already found a better path, best path to it, optimal path to it, which means you do not have to revise that path. So, that the third stage of that revision process we can do away with essentially, that you can be sure that if a node is enclosed, you already have the optimal path to that node essentially, which of course will save a lot in terms of this propagation that you have to do. And in later classes, which is in the next class, we will see that this allows us to design some algorithms which can save on space essentially, but that we will do in the next class. So, let us try to prove this property essentially. So, what are we saying? We are saying that when it picks node n from the open list, at that point g of n equal to g star of n essentially, which is the optimal value. Now, we can rewrite this condition as follows: h of n is less than equal to plus h of n. So, I have just taken h of n to that side, and then I can add g values plus g of m. So, I can add this plus g of m to both sides, the same value I am adding to both sides, so that does not change things. but this one g of m. So, if you look at the figure, g of m plus k of m n equal to g of n, right. So, let me just rewrite this in this order, or in other words f of m is equal to f of n. That is the first observation we make. So, what are we really saying here when we are looking at this criteria? We are saying is that the farther we are from the goal, the less accurate our estimate is, and the closer we go towards the goal, the more accurate our estimate becomes. So, as we move from node m to node n, our f value actually increases essentially. Now, remember the f value is an estimate of the cost of the path going through that node. So, since the path is going through both f and both m and n, the estimate should be ideally the same, but as when you see it from m's perspective, it is actually less than when you see it from n's perspective. And what is the difference? That your n is a little bit closer to the goal. So, that is one of the reasons why this is called a monotone criteria, a monotone condition, is that as you move closer to the goal, the f values monotonically increase. So, since this holds, as you go closer to the goal, the f values monotonically increase. So, that is one observation. So, which holds for any, and by transitivity this will hold for any two nodes on a path from to the goal essentially. So, now let us assume that there is a node n which, so let us remove this, that depicts the search space that we are exploring. So, there is this node n which A star is about to pick, which means it must be on open. So, this is open at that stage of time or that stage of the algorithm, and n is about to pick node n, and we want to make this claim that if A star is about to pick that node n, it must have found the optimal path to n. So, we will do this proof by contradiction. So, we will say that assume that when it picks this node n, it has not found the optimal path. So, assume that g of n is greater than g star of n at the point where it is about to pick n essentially, and we will show that this leads to a contradiction essentially. So, let this be the optimal path let this be the optimal path to the node n, and let us say that, so this is enclosed, and let us say that A star is found some other path. So, this is open, and let us say that A star is about to pick this node n, and let us assume that at that point g of n is more than the optimal cost, and let NL be the NL. So, this optimal path to n, let us say it is this, and NL is the last node A star has inspected on that optimal path, and NL plus 1 is the node which is on open, which is a child of this node, but A star has not expected. So, in what we are saying is that A star has not found this path, which is optimal path, but A star has found this path which may not be an optimal path, we are trying to say. So, n of L last node on optimal path to n, last node seen, and n of L plus 1 is the first node on optimal path which is not seen. So, I am saying that this is optimal path. This of course is one edge, and then there would have been some more edges. That is optimal path to n, and we are assuming that A star has found some other paths to n which is not the optimal path. Now, we can apply this criteria here, f of m sorry. This monotone criteria that we observed, that assuming that the heuristic function satisfies this property, then from any path to the goal this property holds, that as you go closer towards the goal the f value increases. So, as you move from f of this last node n l to n l plus 1 and so on to n, the f value will increase essentially, or at least not decrease. So, in particular we can write that g of n l plus 1 plus h of n l plus 1 is less than or equal to g of n plus h of n. So, I am just expanding this one here and that one there, and I am sort of skipping the transitive steps, and because they are on optimal path, we can replace g with g star. So, we can write g star of n l plus 1 plus h of n l plus 1 is less than or equal to so we can put this star because we are assuming that these nodes, these three nodes that we are talking about, these two nodes n l and n l plus 1 are on the optimal path to n. So, on this path these properties will hold essentially. Now, if this is the case, we can write this as okay, I am just adding plus h n to both sides essentially. So, g of n plus h of n is greater than g star of n plus h of n, and Okay, anyway, that is not so important. What is really important is that f of n is less than or equal to f of n L plus 1. Why? Because we have said that A star is about to expand this node n, and this whole property we want to say that when it is about to expand n, it must have found an optimal path to that essentially. So, this we can write as g of n plus h of n is less than or equal to g of n L plus 1 plus h of n L plus 1. So, I wanted to look at this one and this one. See, I want to basically arrive at this g of n is less than or equal to g star of n using these two, but I have a star sitting there. So, basically I have to put this star here, because we have assumed that in this graph this is optimal path. So, this g of n plus 1 L g of n L plus 1 is equal to g star of n plus 1, which is what I did here. I said I could replace this by the optimal path essentially. So, I can do it here as well. So, now of course, this becomes the same, this becomes the same as this. So, this is less than this, and if you remove h of n, you get this is less than this. But what is this saying? It is saying that g of n is less than the optimal cost, less than or equal to the optimal cost, but that can only be the case if g of n is equal to g star of n. By definition, it cannot be less than the optimal cost, it must be the optimal cost. So, what we have said, so there is a contradiction between this and this, right? Between this and this. So, if you do not even assume this, you can simply show that g of n is less than or equal to g star of n, which you can interpret as saying g of n equal to g star of n, which is the statement we are making here, that whenever it picks this node n, it has found the optimal path to that node, which means g of n is equal to g star of n. And the implication of this, as I said, is that you do not have to revise the cost of those nodes which have been put into closed. Once you put a node into closed, you know that you have the optimal cost to that node essentially. So, we have shown a series of properties about this A star algorithm. The conditions are that the heuristic function must underestimate the cost to the goal, edge cost must be more than some specified amount, some small amount, then A star will always find optimal paths to the goal node. That is what we showed in lemmas 1 to 6, I think, and this is actually lemma 7. The last of the statements that we want to make is that if this, in addition, if this condition is satisfied, then you do not have to keep revising cost to the nodes in close. The moment you pick a node from open and put it in close, at that moment you have found the optimal cost to the node essentially. So, if you go take this figure seriously, then essentially what you are saying is that both these costs are actually of the same whether this path or this path, it is the same cost essentially. G value must be equal to the optimal G value. So, let us compare this with the earlier algorithms that we have seen. In terms of the 4 parameters that we talked about: time complexity, space complexity, quality of solution and completeness essentially. So, as far as the last two of these are concerned, the quality of solution and completeness, we have proved today that A star will find a path to the goal if there is, and it will find an optimal path to the goal. It always so. That leaves the question of time and space complexity. So, again like we said in the case of best first search, time and space complexity both depend upon the quality of the heuristic function. The better the heuristic function is, the lesser the amount of space that your algorithm will explore, and that is what we said here essentially. Now, sometimes what people do is, now unfortunately both space and time requirements have been observed to be large in nature essentially. We will look at examples where space is quadratic in nature. For example, a city, if you imagine a 2-dimensional city, then the farther you go away, you can see the area that you have to explore grows as a square essentially, but the combinations may grow exponentially essentially. And we have seen this property that the higher the heuristic value, heuristic function that you are using, the better for you. But if you want to guarantee admissibility, the heuristic function must be less than the optimal heuristic value. So, what people have often done is that they have tend to use a function like this, f n equal to g of n plus k times h of n. This is known as weighted A star algorithm. So, you use a parameter k to decide how much influence the heuristic function has. Now, notice that there are these two influences on the A star algorithm. G of n is trying to keep it, because we are always going to pick the one with the lowest f value. So, low g means it is close to the goal, low h means it is close to the, sorry, low g means it is close to the source, low h means it is close to the, it at least thinks it is close to the goal. The effect of G is that it tries to keep the algorithm like branch and bound as close to the source as possible. The effect of H is like best first search to pull it towards the goal without any regard to what was the time spent in reaching that node n. So, if you use a parameter like k, you can actually control the effect of heuristic function versus g of n. Now, if you put k equal to 1, then we have this A star algorithm that we have just described. If you put k equal to 0, for example, then you have simply branch and bound. You do not even look at the effect of h. If you put k as very high, which amounts to saying that j is 0, then it is like best first search. It only looks forward, it does not look behind. But if you put a value of k greater than 1, then you are giving more emphasis to the heuristic function, which means that the search will become narrower and narrower essentially. It will be driven more by the heuristic function and less by the tendency to keep track of whether you are finding the optimal path or not essentially. So, obviously, the moment you put k greater than 1, you are losing admissibility essentially, but you can expect that your solutions will be close to optimal solutions, and depending on some trade off that you may have to make, you can choose a value of k higher than 1 essentially. So, very often people have tried 4, 5, 6 values of k and seen that their algorithms run much faster. So, this is simply to guarantee running faster running time essentially. So, what I want to do is to now focus on saving space. This is what people have done after A star was discovered, and it is quite a well known algorithm. We want to look at how we can save on space essentially. So, one of the first ideas that was explored is an extension of an idea that we have seen earlier, which is that do depth first search instead of best first search, do depth first search. Now, if you remember the algorithm DFID, what DFID does is that it does a sequence of depth first search with increasing depth bound, but there we had a notion of a level, because we had no costs associated with edges. So, all edges were supposed to be of equal cost, but since we have graduated to edge costs and we have looked at algorithms like branch and bound and so on, we need a variation of that, and that variation is called ID A star. It was given by a guy called Richard Koff. I do not remember whether we have discussed Koff's work earlier, but he has done a lot of work in search essentially. His PhD thesis, which was in the early 80s, was finding macros. Operators. And in fact, his PhD thesis was available as a book at some point of time. So, if you remember the puzzle like the Rubik's cube, in fact, he was working on the Rubik's cube and the 8 puzzle, and we have seen that it is very difficult to devise heuristic functions which will drive hill climbing like algorithms towards the solution. So, what we tend to do is that we have this set of macro moves, which says if you have done the top layer, then if you want to do, let us say, the next objective, which is to get, let us say, one kubelet into place in the middle layer, you say do this sequence of moves, left, right, left, up, down, whatever, you have some notation for that. That is a macro move. A macro move is a sequence of moves packaged into one abstract move essentially. The question is, how do you get macro moves essentially? Of course, most of us learn from friends, but what Koff did for his PhD work was that he wrote an algorithm which will search in the Rubik's cube problem and the 8 puzzle problem and try to learn macro moves essentially. So, his algorithm actually built a macro table, which of course, once you have a macro table, like we solve the Rubik's cube, we do not do any search. We say, okay, I will do the top layer first, then I will do the second layer, then I will do the third layer. Koff's PhD thesis was to build that table which listed all the macro moves essentially. But this IDA star is also by Richard Koff, and we will see a bit more of him as we go along. This was in 1985 or so, and IDA star stands for iterative deepening A star. So, it is still A star in the sense that it guarantees the optimal solution, but it is iterative deepening like DFID was essentially. So, the algorithm idea is very simple. What it says is that if you are at the start node, you create a boundary. Now, first let us see what DFID would do. You ignore, because it does not see the cost of an edge, it basically sees it as level by level. So, it would first do depth first search up to some level, then up to some next level, then up to some next level. So, we are assuming that edges are sort of roughly similar in cost and so on. So, even if you have edges of equal cost, IDA star has some value. So, DFID would have basically expanded its search space gradually, and if this is a goal node here, it would have found eventually at one of the expansions, it would have found a path to goal, and since it did not find it in the previous round, it means this new path must be the shortest path, because it is only in this last iteration that you extended this depth by 1, but it uses linear space because it does depth first search essentially. IDSR is basically a variation of this. It says that you draw a boundary which you use for controlling your search, and the boundary is essentially those nodes, well, it should not come here, should fall short of this actually, something like this. Okay, so it may not, just to depict this essentially. So, this is a curve which is defined by f star of s. So, this is the locus of f star of s, which means all the nodes on this boundary have value equal to f value equal to the optimal cost essentially, and the optimal, sorry, not f star of s, f of s, the estimated, because you do not know f star of s, you know f of s, and that is the estimated cost from start to goal, as which is equal to h of s incidentally, because g of s is 0. So, these are the nodes whose f value is equal to that value h of s, and nodes inside have lesser value and nodes outside have greater value essentially. Now, one of the things that you should observe is that this boundary is lopsided, it is towards the goal, and that is because it is using a heuristic function essentially. Nodes which are closer to the goal will have lower heuristic value, whereas nodes which are away will have higher heuristic value essentially. So, what idea star is that in the first iteration, so you said depth bound, well depth is not the value, let us say bound, it starts with saying bound equal to h of s, and it does DFS it does a DFS as long as the h value is f value is less than the bound. So, it is like a boundary it has drawn for itself, and it is saying that I will within this boundary I will do depth first search. So, let us say it explores a node here, it may have some children here, another node it explores here, somewhere here, let us say it may have some child here, another node here, it may have some child here, and so on, and all of them will have their f values that you would have computed. If it does not find a goal in this depth first search, now this is depth first search with a bound that the f value, so it cannot go off in this direction, it cannot go off in this direction, so only has to stay within this boundary. It augments this boundary by another boundary which is little bit bigger than this. So, increment so, for the lowest f value of a node which it is not picked, which is means it is beyond the boundary, it increments a bound to that and then puts this into a loop essentially. So, you can see it the similarity with DFID. In DFID, if you did not find a path to the goal, you would increment the level by 1 and then try DFS again. What this is doing is it increments the bound to the next. So, with all these nodes which it has, so this is explored, but all these nodes which is not explored, generated but not explored, it keeps track of what is the lowest f value and increments the bound to that in the next round and does another depth first search, and it repeats this process till it finds a goal essentially. So, what do you have to say about this algorithm? First, we should convince ourselves that it is admissible, it is worthy of that star on top of the name, that it will guarantee an optimal solution. Can you argue for that? Well, when it starts with a bound which is equal to h of s, and given that h of s is an underestimating function, it is not possible that a path of length greater than the optimal cost will exist within h of s, because h of s is an underestimating function. If the actual cost of going to the goal is h star of s, h of s is less than h star of s. So, this boundary will never take you to a node which is more expensive than the optimal cost. If it does not find a value with, if h of s was perfect, then within the first iteration itself it would have found a path to the goal. But if h of s is not perfect, it would just be short of goal a little bit, and then you are going to increment the bound. Okay, so, I have not written the word increment here, but it is the lowest unexplored. If you can read this word is supposed to be unexplored, the lower unexplored f of n prime, where n prime are all these nodes which have not been picked essentially. So, because it is only incrementing the boundary to the lowest unseen f value, if it finds a goal of f that value, then it will be an optimal cost, because it is only making very conservative increments, it is guaranteed to find an optimal path. But you can imagine that in a search space like this, the number of iterations that it will have to do is going to be very many essentially. So, it is going to be optimal, it is going to save on space. Why? Because it is depth first search, it is a sequence of depth first searches which only requires linear space, but its time complexity is going to go up by many times, because it will do many iterations essentially. So, some variation that people have tried is that instead of incrementing it by to the next lowest unseen value, increment it by a fixed cost that you are willing to bear essentially. So, some delta. So, instead of this, if I write bound it means that I am making a bigger jump in this essentially. So, that means let us say this is my next value. So, let us say this is plus delta. So, this was the original bound and this is bound plus delta. What is the danger here? The danger here is that there may be a goal node just beyond this, but there may be a goal node here, and because it is doing depth first search sweeping the space like this, it will find this goal node, but it will not find this goal node. This goal node is cheaper. I mean, if you just assume that this is kind of to scale in some sense, this node is cheaper than that node, but because it is doing depth first search sweeping the space like this, it will find this goal. But this, of course, this delta allows you to control how much suboptimal you are willing to go essentially. So, this distance, this is delta that you have increased the boundary by, basically says that in the worst case you may have optimal cost plus delta, but in this big jump you would cover many nodes. So, the number of iterations that you do would drop essentially. So, it is nice in the sense that it takes linear space essentially, and it guarantees an optimal cost. So, it is an extension of DFID in that sense, which uses this fact that there are edge costs and there is a heuristic function and things like that. So, what is not nice about this algorithm is what was not nice about the original algorithms. The blind, it is a blind algorithm now essentially, except of course that it has a boundary that it draws which is determined by the heuristic function. It is uninformed, it does not move towards the goal, which is why we started with best first search in the first place. This is which is why we use the heuristic function in the first place, but this is not exploiting the heuristic function. It is using the heuristic function only to determine this boundary essentially. So, in the next class we will look at another variation which exploits the heuristic function and which is also a linear space algorithm. That algorithm was also given by Richard Koff. Maybe if you want to think about that a little bit essentially. It is a little bit like saying that it is hill climbing with backtracking. If you can think of along those lines, the algorithm is like hill climbing, but it is allowed to backtrack essentially and then try another path essentially. So, which means it will not have exponential space, it will have only one path always in the memory. We will look at that algorithm in the next class, and then we will look at some more recent algorithms which have come in this century, I should say, which are space saving algorithms, which are quite interesting essentially. So, I will stop here for today.